Too large. That would solve it for us.
Nobody wants to come back to solve the quiz.
You don't have to commit to work somewhere. You're not yet large enough.
So any takers for what is it? What's this one compute? Well, yeah.
Number of paths?
The number of paths with X and Y for the first one.
Okay, and how many are there?
One.
Is this true? Give me a second. So we take what is the root n? What is the root present? Right, because if you look at what happens at n minus 1, that should be n minus 1 times 1, and plus 1 is n. Inductively, you can prove that the length is n. Interesting. So it is n. It's not a number of paths. It's the length of the path, essentially, what you're getting here. Can you take it for the second? This is Fibonacci. Very interesting. This gives you the Fibonacci sequence. Amazing what you can do with data log. And the last one is really hard. These are the Catalan numbers. So data log over semirings is really, really fun. But now I need to switch slides to talk about termination.
Can you go to the previous slide?
Okay. Let's start with Paris.
So this is really bizarre because the first and the second we kind of know for they're equivalent, right? It's the nonlinear and linear transitive closure. But when you interpret them over the sum, they give you different.
Yes. So
so they're not equivalent in that case.
They are no longer equivalent because we don't have the idempotence. You're thinking about the semiring of Booleans,
yes.
And the standard data log works over the semiring of Booleans raised to the right power, to a big power.
Yes.
While here we have the semiring of natural numbers.
Okay. So in that case, then linear and nonlinear programs are not the same.
They are no longer the same. Yes.
Even in power series, you'll find the Catalan numbers with the nonlinear.
Even in the Boolean, linear and nonlinear are not the same.
Even as a Boolean.
It's not true that every nonlinear program is linearizable.
No. But if you take transitive closure, you can derive it as yeah. I'm talking about this specific example. Yeah, this specific example.
I see. So no, Paris has a point. So this program over the Boolean should be equivalent to this one. This is what Nicole showed us yesterday when she did the squaring of the matrix. And you can do this apparently much faster. Actually, for data log, doing the nonlinear, implementing the nonlinear program turns out to be slower. And I think Hank and Mahmoud, they know much more about this. Usually the nonlinear one requires more work. But they are equivalent, and the nonlinear one takes fewer iterations. Yeah, so discussion. But as Paris points out, over other semirings, we have to be careful. They are no longer equivalent. Yes, Pierre.
I'm not sure about the first example.
For me, the first example computes with a number of paths.
Yeah.
If the counting provenance, so it's the back semantics for the natural data log program that.
Okay, so let's say you're right. So let's say that t of x, and start with x from 0. X is 0. So t of x and k is equal to 1.
Yeah.
So then t of 0 and minus 1 is 1.
Yeah.
But then what is t of 0 and n?
It's 0 plus 1 times 1.
No, it's 1. This is.
No, this is 0.
There is no edge. You're right.
Yeah.
The best way to make sure your audience is awake is to have mistakes on your slides. and this was an honest mistake. I really thought it then.
Following Paris's question, do you know if the last program is equivalent to one that is linear?
Well, at this point, I don't know anything anymore because. But yeah, you see, it's interesting. It's not. These are non-trivial.
That's where Hilbert comes into place. We must know, we shall know, right?
We must know, we shall know. Yes. But I really want to focus on termination because there are so many interesting things we can discuss here. I just need to find my slides. So this is the purpose of the second lecture, to discuss termination of the naive algorithm. When does this happen? Just to quick review, so we love data log, the standard data log, because it has a well-defined semantics. It always terminates in polynomial time, but it only works on sets under on sets and positive operation, not monotone operations over sets. So we looked at a partially ordered pre-semiring, and we extended data log to partially pre-ordered semirings. And this is what we call data log with a ring here as a top, data log O. And importantly, we actually don't need to care about pops because convergence happens in the core semiring. All the values over a cycle, they are confined to this core semiring, which is naturally ordered. So we can restrict the entire discussion, this lecture, to naturally ordered semirings as we analyze convergence. Okay, so the right framework to study convergence of data log is that of polynomial equations in a semiring. Polynomial equations have been, they occur in many branches of mathematics and computer science. And as Val mentioned, actually, back in the 50s, the semirings were studied in the context of formal languages. And in formal languages, a grammar is essentially a polynomial equation in a non-commutative semiring. In the non-commutative semiring of all languages, or all the regular languages, where the plus is union and the multiplication is concatenation, so it's no longer commutative. We will discuss only commutative semirings, and it turns out that the least fixed point of a data log program is equivalent to the least fixed point of a set of polynomial equations, namely that those obtained by grounding the data log program given the atoms in the input, given the constants in the input EDB. So this is what I plan to do next, to discuss polynomial equations in a naturally ordered semiring. Okay, so we fix a semiring. For now, it doesn't have to be naturally ordered, but we still need it. We fix a set of variables. They are blue because they will correspond to the IDBs. So this is something we want to compute. They are not given. And a monomial is what you expect. It's a product of variables to powers. And a polynomial is a sum of monomials multiplied with coefficients from our semiring. So here is an example, a simple polynomial in two variables. And S of x, this is what Val also introduced yesterday, is a set of polynomials with coefficients in S and with variable x. Okay, what is a polynomial equation? It's actually a set of polynomial equations. We have n variables, and we have an equal number of polynomials, f1 to fn. And we are looking for a solution to this system of equations. And the terminology, I will call it a polynomial equation, although it is a set of polynomial equations. In short, x is a tuple of variables, f is a tuple of polynomials, and we say we are looking for the fixed point, x equals f of x, where f now maps from s to the n to s to the n. Of course, we can compute the Kleene sequence, assuming now that S is naturally ordered. Now we need to assume it's naturally ordered. So we start from 0, because in a naturally ordered semiring, 0 is the bottom. And we repeatedly apply F. We get this increasing sequence. That is our Kleene sequence. And now we know all the theory. If the semiring is omega continuous, its least upper bound is the least fixed point. Because in an omega continuous semiring, we require the operations plus and times to be omega continuous, and therefore every polynomial is also omega continuous. Okay, example.
So
Yes.
do you need which is about monotonicity?
Oh, yes, but that is a consequence, it's not a definition. And in any naturally ordered semiring, the operations plus and times are monotone. And therefore, every polynomial will be monotone. Thank you, Floris. Super important. This is how things fit together. It's fun to look at polynomial equations, and here is a little secret. The most important polynomial equation is this one. It's 1 plus ax, is x equals 1 plus ax. I wrote it on both whiteboards because we need it repeatedly. So how do we think about solving this? Well, we compute the Kleene sequence, and it looks like this. We start from 0, we apply the function once, the second time we get this increasing sequence. And if this converges, if it's finite, then that is a least fixed point. If it's infinite, maybe we have a least upper bound. We know how to think about this. But using pen and paper, how do we think about the solution of this equation? Well, we solve the equation at the top, as you would do in high school. You just say, well, x is 1 by 1 minus a. And then we expand this as an infinite series. And that formal power series is the solution to our linear equation in an informal way. Okay? This is how we solve a polynomial equation. What about a quadratic one? What is a Kleene sequence now? Well, it's more complicated. So we start from 0. We plug in 0. Now we get b. The second one is b. We plug in b here. We get b plus ab squared. And it gets messy pretty quickly. So how can we actually solve this? We do the same thing. Like in high school, we solve the equation. We get a non-algebraic expression with a square root. And now we can expand the square root as an infinite series. And guess what? The Catalan numbers show up here. Very interesting. So now you have the feeling that you can solve any polynomial equation not so quickly because this little trick only works for degrees up to 4. Beyond 4, we don't have closed form solutions for polynomials. So in general, polynomial equations, they tend to lead to power series, but it's not always the case that we can compute those power series. Yes, Remy?
I got decided, but where do division and minus come from and like square root?
Where does the minus come from? That is what I'm shifting under the rug. Think of this as a back of the envelope calculation, and I don't claim to prove that this will lead you to the correct expansion, but I'm pretty sure it's right. That this power series is indeed, in a formal sense, the least fixed point of this equation. Yeah, in a way in which I can make formal in a bit. Okay, so take this as a method to just do back of the envelope calculations for polynomial equations. Okay, good. So a quick discussion. In order to ensure that this least fixed point exists, we need to require S to be continuous. As some of you have pointed out, how do we make sure that S is omega continuous, or how do we extend it to make it omega continuous? And there is actually a general way to do this. For every naturally ordered semiring, there exists, unique up to isomorphism, freely generated omega continuous semiring, which I'm going to denote with S to the power omega. I'm pretty sure this is a classic result, but it's so easy to prove that I just put it here on the slide. So the algebraic, the formal property that this freely generated omega continuous semiring satisfies is written here. So we have it comes with an injective function from S into this extension S infinity. And it has a property that for any other omega continuous semiring, if you map from S into S prime, then you can uniquely extend this function into an omega continuous function from S infinity to S prime. It's a mouthful. Just forget it. Let's look at the example. This is the proof how you construct that thing. And I'm not going to read it, but I'm going to ask you, if you start with the natural numbers and you want to compute the freely generated omega continuous semiring of the natural numbers, what is that set? It's just n using the infinity. That's all you need to add that infinity at the top. What about polynomials? We start with polynomials. This is a naturally ordered semiring, but it is not omega continuous. You can construct bigger and bigger polynomials by adding more monomials or increasing their coefficients, and this can grow forever. How do we ensure that? How do we complete the semiring to make it omega continuous, omega complete? Power series, but also the coefficients. We need to allow them to also be infinity. Okay. So this has a consequence. If we start with any polynomial equation in a naturally ordered semiring, then we are guaranteed to have a least fixed point that lives in this freely generated omega continuous semiring. This is algebra, so it guarantees something exists. It doesn't quite tell us how to get there and how to represent it, but at least we know that it exists. Good. So I think this is all I wanted to say about polynomial equations. We will see more about this later on in this lecture. But I want to show you how to apply this. What is the connection between a data logo and polynomial equations? And this is what we call the grounding of a data log program. Grounding is such a simple concept that I only have one slide for it. We start from a data log program. We start from an input EDB. These are all the relations that are given to us, all the input relations. And the way we ground it is that we construct, we choose n variables and polynomials, where n is a total number of IDB predicates that we can construct using the constants from the input. Okay. So the input was our database. Maybe it consists of all the parts and their subparts. Maybe it consists of the nodes in a graph. And it has a finite set of constants. Out of those constants, construct all the ground atoms that you can construct using the symbols in the IDBs, the ones that you want to compute. This gives you an upper bound of what your program can compute. Call that thing n. And for each such potential output tuple, introduce a fresh variable x. Our goal is to compute the value of that output tuple and the value of that x. And that is given by a set of polynomial equations. A quick example together, actually the example comes on the next slide. The most natural, let me put it this way, a special case of grounding is when we assume that each input tuple of the EDB is annotated with an abstract variable that represents kind of the provenance or the source of that input tuple without committing to any particular value in a semiring. And if we do this, then we have a second set of variables. This is where it's a little bit dangerous because it can become confusing. These variables, they represent in an abstract way the values that we get from the input EDB. what we want to compute are the blue ones. These are the values of the IDBs, the ones that we want to compute. And then a program that has a relatively small set of rules gets grounded into a possibly much larger set of polynomial equations, where we have one polynomial equation for each possible grounding of an IDB, and the corresponding f is obtained by grounding the rule of the body of that program.
Then are you looking at all possible IDBs here? This is all possible IDBs?
All possible IDBs. Yes, Val.
Yeah, so actually, I don't remember if we actually stated this in our paper, but we found that if you first solve the data log program in set semantics, then you actually need only those IDB tuples that are in the solutions of the set semantics result. No other IDB tuples, in fact, occur in the system of equations. And that, in practice, if you want to show an example, it makes a huge difference.
I actually wasn't aware of this, but it's a very cool observation. So I was conservative here, and I said N are all the IDB tuples you can construct, but you can't be conservative. You just run the data log program in a traditional way, and that gives you already a more restricted upper bound of the tuples you care about. Very nice. And the solution to these polynomial equations, which started from this abstract tagging of the input, they were called provenance power series in the original paper by Rinkarno-Barakis and Val. I think you can think of them as generalization of the provenance polynomials that you get from for non-recursive queries, for conjunctive queries and unions of conjunctive queries. Okay, I want to show an example because that gives you a lot of intuition. Here is our very abstract data logo program. So intuitively, it computes the single source shortest path from A, to every node X. But it doesn't have to be single source shortest path. It can also be sum of subparts, sum of the total cost. Can be anything here because I didn't commit to a particular semiring. The input relation, the input IDB is E is given by this little graph here. So there are three edges, three groundings of the relation E. And the way we compute the provenance power series is by first introducing abstract taggings, the black ones, the Z's, for every input atom. These are probably concrete numbers, or maybe they are Booleans, whatever they are, but we are going to give them an abstract name Z. In addition, for every potential output tuple, and there can only be two, R of A and R of B, for every potential output tuple, we are going to give them new, fresh names, X1 and X2. And then we end up with two polynomial equations, one for X1, one for X2, which are obtained by simply grounding this program. A solution which now we know how to compute. We just eliminate variables, compute the series, and we get these power series. The solutions, which are these two power series, are the provenance power series of the output tuples of this recursive program. Okay, very cool. It kind of gives us an abstract way to talk about the value of any data log program. Wolfgang, you're confused.
Are you gonna say that you're being quite cavalier solving these equations, and as if they were algebra, but in fact you're using something called packages theorem to justify that that you can solve them with substitution in the usual way?
So right now, I'm only solving them in the set of power series. So they are solutions as power series. If you want to solve it in a concrete omega continuous semiring, then you use the fact that the set of power series is a freely generated omega continuous semiring, and you use you evaluate that power series in your concrete omega continuous semiring. And I wasn't planning to talk about that. Yes, Wolfgang.
So the question you is, can you also do some normalization in this? What the wondering is like, could you do like PageRank? Can you do personalized PageRank as a fixed point of something where you also distribute flows in a network, but then you somehow want to normalize in different steps? This is not just here, but just.
I actually don't know. It's something that I would try. I don't know. Yes, Guy?
In light of Paris' earlier remark, is it then the case that the linear and the nonlinear transitive closure program have different provenance power series?
Yes.
Yes. So one of them comes from Catalan numbers, the other one has.
Interesting.
Yeah. Very good observation. So this is where you can see the difference.
So will they always have a solution for the identity variables in the system application?
Yes, they will always have a solution in the semi-ring of power series, of formal power series. This is the power of algebra. You are guaranteed to have that solution. It's a least fixed point. It's a least fixed point of that set of polynomial
But
equations.
you can't necessarily find it.
But we don't know how to find it. That's a big question. Yes, Paris.
Ask about the computability of these things. So can we actually have do we always have closed form solutions for that, or?
No. So once the degree exceeds 4, then it's over. I don't know how to compute it.
Right.
However, we can always run the naive algorithm. This is where I want to get. Yes.
There are actually some marginal, as I can say, so results in our original paper. You can actually, for a fixed monomial, given the system of equations, which is a finite input, you can actually compute the coefficient of a fixed monomial.
Okay.
In the full power series. That's going to be a natural number. There are other questions which are undecidable. So, for example, because you can see things about contact grammar represented this way, you may recall that whether a contact grammar is ambiguous is an undecidable question. So, if you actually have the patience to get to the last page of our paper from 2007, you'll see some stuff.
I got you, and I can confirm. So, indeed, with what Val proves here, and this discusses is that indeed any finite property you can imagine over these power series, you can actually answer. How you answer it? I mean, they have smart algorithms, but I'm not so smart. I would simply run the naive algorithm until you stabilize it so that it's at a monomial, and this is how you answer it. Okay, so. Good. So so we have these abstract power series that are the abstract solutions of polynomial equations. But how do we compute them? The old data log systems, the way they compute, they evaluate data log is using the naive algorithm, is by computing the Kleene sequence. And the question is, when does this Kleene sequence terminate? When does a naive algorithm terminate? That is the next question to address. And this is where it gets, in my opinion, this is where it gets really interesting. So when does it terminate? And the message will be that this depends on the algebraic properties that we have over the semiring. And I'm planning to discuss 4 algebraic properties. And eventually there will be one of them that is necessary in condition and sufficient for termination. So the 4 algebraic properties are dioid, absorptive semirings, stable semirings, and non-uniformly stable semirings. As always, we are going to denote with M the number of EDB atoms. These are the given values to us. And denote with this blue N the number of IDB atoms. These are the unknown variables that we want to compute. Okay. The first concept is out of a dioid. So a dioid is a semiring that satisfies this identity. 1 + 1 is equal to 1. This is the most boring dioid. I should have replaced it with a more interesting one. This has this property because OR is 1 + 1 or 1 is 1. Some simple properties. Every dioid is idempotent. Addition is idempotent. Because if you multiply this with X, then X plus X is equal to X. In a dioid, bizarre things happen. this tells us that 2 equals 1. If 2 equals 1, then we also have 3 equals 1. We have 2 equals 9. We have all sorts of things. Diodes are bizarre. Interestingly,
Means 3 equal 1. So 3 is not part of the set. What does this mean? 3 equal 1?
3 just means 1 plus 1 plus 1. If you add 1 3 times, I abbreviate that to 3, and that means 1 plus 1 plus 1. Interestingly, every diode is naturally ordered, and the natural order can be defined as x is less than y if and only if x plus y is y. Carl mentioned this, and it's equivalent to saying that plus is the least upper bound of 2 elements. Okay, good. So what happens if our semi-ring is a diode? Does every data log program terminate? Does every data log program on a diode terminate? And the answer is no. You can kind of get this by thinking about how the freely generated diode looks like. And that is an example of a diode that is as bad in terms of termination as any other diode. And that, if you remember from Val's slides, that consists of polynomials over these variables z, where all the coefficients are 1. We cannot have coefficients 2 because 2 is equal to 1 and 3 is equal to 1, or every natural number becomes equal to 1. Yet we can have an infinite increasing sequence, and this is the result of our simplest equation, this one here, except that A now is the z over there. And therefore, even the simplest polynomial equation will diverge in the freely generated semiring, which I forgot how it's called in the freely generated semiring. The set of polynomials of B of C. Oh, I don't think I have a name for it. This is
polynomials with booleans as coefficients, but that just simply means that it's a sum of monomials. Some are there, some are not. Right?
Yeah, that's exactly.
No coefficients. But it is the freely generated idempotent monoid, where idempotent means for plus.
Yeah, this is a
or
freely,
dioid as some like.
yeah, the freely generated diode. They're actually also called ordered monoids because you can retain just the times operation, and then the plus operation is just a consequence of the order. So they are, you can also view them as ordered monoids. Good. Attempt number 1 didn't help us too much. Attempt number 2, so the Kleene sequence may be infinite, doesn't help us. Attempt number 2, absorptive semirings. A semiring is absorptive if 1 plus A equals 1. This is an identity in the absorptive semiring. And Valor already mentioned this yesterday. A typical example, okay, first of all, every absorptive semiring is already a diode because you can simply replace A with 1 and it's a diode. So it is naturally ordered. Okay, so far so good. I think Baldi noted with SORP
but with round parentheses instead of square. So but first of all, it's a horrible name, sorry. But you want to put square parentheses only when it's actually polynomials with some coefficients from some semiring. I try to do that. When it's otherwise some construction and just depends on some set of variables.
Right. So, but what I'm saying is that this notation should indicate that this is a set of polynomials. Well, it's not quite. It is a set of polynomials where we do some identification. And what we need to identify these. We need to identify if one monomial has strictly has larger degrees than another monomial, then the second monomial, the first monomial is absorbed. You factor out and it's absorbed. So we can only have terms that are not absorptive. Anyway, this is how I like to define sort with or without round parentheses. Interestingly, this set satisfies the ascending chain condition. This is a non-trivial exercise. Okay, try to prove that this set of absorptive polynomials satisfies the ascending chain condition, but it does not have a bounded rank because you can z is less than 1 for the simple reason because z plus 1 is equal to 1, and therefore z is less than 1. And therefore, you can construct these longer and longer chains starting from d to the k, going all the way up to 1. And this semiring does not have a finite rank. However, it turns out that the Kleene sequence of n polynomial equations has rank n. You apply the naive algorithm, and you can only need to run this for n steps. This might have been known, but I don't think we have found this in the literature. This particular statement. Okay, so this is already a success story. If your semiring is absorptive, then your data program will terminate in a number of steps, which is less than or equal to the number of ground IDB atoms. Yes, what do you think I'm happy? You're happy. Okay. I wanted to make here a comment. The polynomial equations can be thought of equations in a product of semirings, of naturally ordered semirings. But the problem is that the product of absorptive semirings is not necessarily absorptive. So in order to prove this requires some sweat. It doesn't follow from simple product properties. Yes, Paris?
We can discuss this offline, but I think maybe this is a consequence of Valls and Suldipa's ICT 2014 paper, because there they construct a circuit that works for absorptive polynomials, and the circuit has n steps. So I think that could mean that probably this is like consequence of that.
Yeah, I wouldn't be surprised.
Yeah.
But we got it as a consequence of a more powerful theorem that I want to show you next. So let's talk about stable semirings. And the motivation for this is, if you remember, the most important polynomial equation, which is this one. So as you compute the Kleene sequence, you get these sums of powers of A. There is a notation which was, we know it is from the book by Mondrian and Minou and Gondrian. Mondrian and Minou. So A to the power parenthesis P is the sum of all powers of A up to the power P. We are going to say that a semiring is P stable if for any A to the sum of the first P powers is the same with the sum of the first P plus 1 powers. The same as saying that the Kleene sequence terminates after P steps. It's just an algebraic condition. Are there such semirings? And the answer is yes. Here is a really cool one. This semiring consists of bags of P plus 1 elements of non-negative real numbers. The addition consists of taking two such bags, takes their union, and retain just the P plus 1 smallest elements of the union. The multiplication consists of taking two such bags, take all pairwise sums, retain the P plus 1 smallest elements, never exceed P plus 1. Why is this semiring interesting? When P is 0, then this is exactly the tropical semiring. Then we only have bags of size 1, and the operations are min and plus. When P is not 0, then this semiring allows you to compute, like think about all pairs shortest path. It allows you to compute the p+1 shortest path from x to y. So this is a semiring you want to use when you want to compute the p+1 shortest path. Okay. Interestingly, and I don't think I wrote this on the slide, every p-stable semiring is naturally ordered. This is surprising. Just this condition here for every fixed p guarantees that the semiring is naturally ordered. Okay, so what do we know about this? Notice that it is no longer omega continuous. I hinted there why it's not. So what we proved is that the clean sequence of n polynomial equations also has a finite rank, which is a pretty ugly expression. And we couldn't improve it. We don't know. We don't think it's tight. We know that you cannot simply replace here p plus 2 with p plus 1. But it is, at least we have an upper bound on the number of iterations that the clean sequence can take.
What do you see to not the expression?
Sorry? I was hoping for better, but it is exponential, yeah. It's no longer linear. This is the problem. So we cannot guarantee that the data log program terminates in polynomial time, because if p is like 5, then this gives us an exponential running time for the data log program, and that is what I don't like. Okay. Yes, and the annoying part of our proof on the theorem is that we had to deal as a special case for when p is 0, because when p is 0, we get the absorptive semirings, and we want this to be n, but this formula doesn't give us n. We had to go through extra effort to recover that result. When p and when the data log program is linear, then you can put here p plus 1, very strange. But again, that requires a specialized treat in the proof to show that in that case you can put here p plus 1. Okay, so is that a necessary condition for termination? And the answer is no. Here is a necessary and sufficient condition for that guarantees that every data log program terminates, or that every clean sequence of a set of polynomial equations is finite. And the condition says that for every a, there exists some p, which depends on that a, for which the a to the power, the sum of the first p powers of a is equal to the sum of the first p plus 1 powers of a. Just a brute force way to saying that clean sequence of the simplest polynomial equation terminates for a, in a number of steps that might depend on a. Okay. So there is an elegant semiring which I actually don't have time to describe. I don't know if there exists a freely generated stable semiring. So I don't dare to talk about polynomials that come from this set, because I don't know how they look like. However, we proved that S is non-uniformly stable if and only if the clean sequence of any polynomial or any set of polynomial equations is finite. One direction is trivial. Of course, if you want all these equations to terminate, then every element needs to be stable. The other direction is hard, proving that if every element is stable, then when you go to higher degree polynomial equation, then they still terminate. Yes, Paris.
So this result says that I can find there is some data log program for which it doesn't terminate, right? Yes. Can we say something about like a specific data log program? So is it possible that you have a non-stable semiring and a recursive data log program and you just have termination?
It is possible. So we did not look at anything specific there. Okay. Okay, so taking that result and moving it to data log results in a statement that's actually totally unsurprising. It just repeats what we saw before from polynomial equations to data log. And I prefer not to talk about this because I have two more interesting topics that I would like to cover, and I only have like 16 minutes for two classical topics. The takeaway so far, and this is, I think, is the most important takeaway, that specific algebraic properties of the semiring, they allow us to reason about the convergence and the runtime of the naive algorithm of data log over that semiring. And I think that is nice. Most of the runtimes that we have are probably not tight, so it's an open problem how to extend how to improve them. I did not discuss the semi-naive algorithm. We have some small progress in this direction, but this is, I think, it's still an open discussion. And I had to take out this beautiful technique that replaces a naive algorithm with a different method, replaces a Kleene sequence with something that's called the Newton sequence that was developed by Esparza. But Esparza will be here during the third workshop, and he's going to hopefully talk about this topic. What I want to discuss next in only 15 minutes is the use of a closure operator. Okay, so let's talk about the closure operator. What is a closure operator? It is a unary operator that you add to those two that you already had in the semiring, denoted A star. And the intuitive meaning, but it's not a definition, but that would be the intuitive meaning, is that A star is this power series. Remember the most important polynomial equation. You want to have an explicit solution for this most important polynomial equation. That is the intuition behind the power series. So the question is, if we have this, can we use the closure operator to find explicit solutions to every polynomial equation by applying star? Now, you already know that the answer is true for regular expressions, right? If you have regular expressions, you can define them as polynomial equations, and you can always convert them into an explicit expression that uses star. So there are two beautiful classical results from the literature that extend on that observation. One is on the linear equations in closed semirings by Lehmann. It's an absolutely beautiful paper. And the second absolutely beautiful paper on polynomial equations in linear algebras, in commutative linear algebras, I should say, by Hopkins and Cousin. First one, closed semirings by Lehmann. His motivation was that he observed back in the 70s that several algorithms used a similar structure and a similar correctness proof, like Warshall's algorithm for the transitive closure of a Boolean matrix, Floyd's algorithm for the minimum cost path, or even the Gauss-Jordan method for inverting a real matrix. And he introduced a very simple notion of a closed semiring, and he proved that all these algorithms can be presented in a unified framework in this closed semiring. I'm not going to describe the algorithm, but I'm going to describe the closed semiring and the key technical contribution of that paper that allowed him to describe this algorithm. So what is a closed semiring according to Lehmann? It is a not necessarily commutative pre-semiring with this additional unary operator that satisfies just these two identities. A star is equal to 1 plus A times A star. And since it's not necessarily commutative, you also write that it's equal to 1 plus A star times A. That's it. So the most, yes, Val?
I have to warn everybody that the name is confusing because there is a concept of closed semiring that means something completely different that some of you may recall from reading from the data structures and algorithms book of, I think, Ullmann and Echo and Ullmann, right? It's a special definition.
This one.
This is called the star simmering. So the reason I kind of committed on this name without too much excuses because Kozan actually makes a good point that Ullmann's book defines this operator in a complicated way, but at the end, they only need a star operator with essentially these axioms. Yeah, so but I should acknowledge that the term closed semiring is not as cut in stone.
In Conway's book, there are also some notion of closed semiring that it's not quite.
And the closed semiring is sometimes what you call stable semiring also.
Oh, interesting.
The terminology of semiring is
Very all over the place. Okay, but let me show you why I find this super cool. Because of everything that is not required. So he doesn't require it is to be a semiring, it's a pre-semiring, although he doesn't call it this way. He calls it a semiring, but he insists that we do not need this identity. He doesn't require commutativity. There are some expected identities that we expect, but he doesn't require them, and they do not follow from the identities of a closed, what he calls a closed semiring. And there is no need to require the semiring to be naturally ordered. And I believe that you can find examples which are not naturally ordered, but I can get it. Okay, so what do we do with the semiring? Well, he talks about matrices. So he's going to solve linear systems of equations. So matrices are the key technique to reason about linear systems of equations. And we have to be careful because the matrices, they do not immediately form a pre-semiring. The problem is that multiplication with the identity is not equal to A. This is something that Lehmann points out. Why is it not equal to A? Well, because we're missing the absorption rule. So when you multiply the terms you don't need with multiplying them with 0, they don't disappear.
What is the star operator for matrices?
That is the main result. So I do not claim that they form a closed semiring, but I will claim it right now. Okay. What Lehmann proved, and this is a beautiful result, is that there exists a construction which gives us a closure of a matrix, which satisfies exactly the identities of a closed semiring. And the way he proves this by explicitly describing the closure of a matrix. He says, take your matrix, divide it any way you want, such that the diagonal block matrices are squared. And he simply defines it, boom, the A star is equal to this definition here, and you can use the closure of the smaller matrices because it defines them, you construct them inductively. So Grace, you don't need to write them. It's way too long. I can send you. I can. Sorry, I didn't mean to interrupt, but for me it's a pain to write that formula. So I don't want others to suffer through the same pain. So what does
closure of the induction step? So what's the closure of a single value?
We have the basic closure operator, and this is what we use for the base case. That is A star. Because you live in a closed semiring. Yeah. And the beauty of Lehmann's theorem is that he extends this from single elements to matrices. So he proves two main results. A star is well defined. We don't care about how we split it. We get always the same result. And moreover, the closure of a matrix satisfies the same identities of a closed semiring. In particular, if you're looking for a set of polynomial equations that are linear, that can be written like this, then its solution is described by A star times P. This requires a verification. You need to take this expression, plug it in here, and then use this identity to prove that it is a fixed point. This is really a beautiful result, so I'm going to wait a few seconds for people to internalize it. Yes, Wolfgang, you're unhappy. You're happy.
So Is this the simplest definition? Because this is related to what was mentioned yesterday. So there is a reduction from all pairs shortest path to mean plus program where you don't lose a log n factor. It's exactly this formula. Because if you want to compute the closure of an n by n matrix, you only need two closures of n over 2 by n over 2 matrices. So you won't lose anything. So I wonder whether there is a simpler definition which is not as efficient but might look simpler.
So I don't know the answer. But I know that Lehmann makes a point of saying that if you add these identities, and I think and there is a second one which I omitted. If you add this identity plus a second one, then you can simplify this definition, and you recover a simplified definition that had existed before in the literature. But as far as I remember, his algorithms are cubic. Right?
Just like Washington.
So I don't know what the answer to your question. Other questions?
Yes. A linear system, I would have thought of it as AX equals B. And this is special form of that.
Okay. Yes. So I should have mentioned this. Whenever we talk about polynomial equations, whenever we talk about linear equations, we always think about fixed point equations. So not AX equals B, but AX plus B equals X. Interestingly, if you look at polynomial equations which are not fixed point, they have been studied. It's a very deep topic in algebra. They are beautifully described in Stanley's book on enumerative combinatorics, volume 2. And I really don't know that area, but there is one fascinating observation there. You need to have solutions. You don't need just power series. You also need fractional powers. You need powers of the form x to the power 1 by n. For the simple reason, because you can say, well, z to the power n is x. So what is z? It's x to the power 1 by n. Beautiful theory. I'm not qualified to talk about that. We only talk about fixed point equations. They seem to be simpler.
Dan, yes, help me understand something. We went from the data log where we wanted the least fixed point to a system of equations. Now this gives us a solution, but how do we go to the least solution?
Yeah, so that is my question. So can we use this to evaluate data log? Because exactly as you pointed out, I didn't write it here, but this is my question, so maybe it comes on a later slide. Can we use this closure operator to accelerate maybe the naive evaluation algorithm of data log to compute the answer of data log in a closed form? And I don't know the answer. I still need 5 minutes to talk about a second fascinating extension, which is Cosen's result on.
What does Lehmann say about data log? I mean, I'm confused now.
1977. 1977.
Yes, no, but how can you apply? What is the implication for data log termination on closed?
I think you can have a closed semiring where if you run the naive algorithm, it will not terminate. The fact that you have a name,
but all these steps you have an explicitly defined fixed point.
Yep.
But that's not the semantics necessarily of the program, right?
Maybe this is a semantics, but if your data log interpreter is given this program and it has a fixed point, it has an explicit solution. But if you start evaluating the naive algorithm, the algorithm doesn't know that there is an explicit solution. It will simply evaluate this sequence, which might be infinite. But that is exactly my question. How can we exploit the fact that we have an explicit construction? Let me show you the second one, because it's really, I hope you will be with me another 5-6 minutes. So The second result that I want to show is about commutative clean algebras. This has actually two motivations. The original motivation for Cozen when he introduced clean algebras was to find a complete axiomatization of regular expressions. I don't know if you remember playing with regular expressions and you get these bizarre identities and you start wondering, well, what are all of them? How can I compute all of them? Well, it turns out, and I know this from Cozen's paper, that Redko proves that no finite axiomatization of all the identities of regular expressions exist. And Cozen credits this to a paper in Ukrainian. Yeah, so I did not read that paper. Let me put it this way. So there is no finite axiomatization. However, Cozen defined clean algebras, which are semirings plus this closure operator. And he showed that if you allow conditional axioms, this was actually known before, but his axioms are very elegant. If you allow conditional axioms like Horn clauses, then they form a complete axiomatization of the identities of regular expressions. Okay, but we are not interested in non-commutative clean algebras, which are necessary for regular expressions. We are interested in commutative clean algebras. And here, Cozen had a second result, which has another beautiful motivation. Motivation number 2. And this comes from Parikh's theorem. So Parikh in 1966, he proved the following, that if you think about languages, but commutativity, you make it, you make concatenation commutative. To say that concatenating two words, you can apply commutativity. Then every context-free language becomes equivalent to a regular language. So for example, here is a context-free language, A to the N, B to the N. We teach this our undergraduates. This is not a regular language. But if you allow commutativity, this is the same as AB star. This is a beautiful theorem of Parikh's theorem. It works for strings. What Hopkins and Cozen did, they showed that this theorem also extends to any commutative clean algebra. So now I hope I have your attention. I need 1 or 2 more minutes to show you the result. So what are these clean algebras? Again, I'm fascinated by the simplicity of an algebraic structure. So a clean algebra is a dioid. It needs to be idempotent. The multiplication is commutative, so we need since it's a dioid, it is naturally ordered, and the closure operator, the star operator, must satisfy these two identities. They're inequalities, but you can convert them into identities, and these conditional identities. The conditional is critical because remember Redko's theorem, otherwise we can't get a complete axiomatization of regular expressions. So this is a clean algebra. So now the result that I want to mention is what Hopkins and Cozen proved in 1999, that if S is a commutative clean algebra, then every polynomial equation has a unique solution. No need to worry about the least fixed point, least prefixed point. There is a unique solution, which of course is also the least fixed point, the least anything you want because it's unique. And the example that they give in this paper is another twist on essentially Parikh's theorem. You take a grammar, this gives you a nonlinear set of equations, but under commutativity, AXB is the same as ABX, and its unique solution is again AB star. Good. So we have seen 2 extensions of semirings with a closure operator. Lehmann's closed semirings, and they are sufficient to talk about solutions of linear equations. And Hopkins and Cozen's commutative clean algebras, they can solve arbitrary polynomial equations. The question on my mind is, Can we use any of this for data log? And I don't have an answer. Okay, and that is it. So let me skip the conclusions because I know we are running late, but I want to leave you with some open problems on the screen, and I will stop right here.
Sorry, I was confused by the example about parentheses. You said the solution is AB star.
I need to go back. This is the language of parentheses, yeah.
And the solution, so it's not the language of well-parenthesized words. So the idea is that it has the same Baryk image.
Exactly. It has this. This language has the same Baryk image as this language. The Baryk image just keeps track of the number of occurrences of a symbol.
Okay.
I didn't check this carefully, but it's in their paper.
Okay.
I thought a little bit. It seems very correct. I don't. Yes, Boris.
So which other things can you say about linear systems? Linear equations. So you put some extra.
For linear equations, we can apply Lehmann's theorem. So there is a matrix. We can compute the closure of the matrix using the star operator, and that gives us the explicit form of a solution. Yes, Albert?
Suppose semiring is also ordered. Can we do linear programming or any kind of that?
I don't know. I should mention that Lehmann in his paper also showed that with the same framework he can capture the inverse of a matrix. And for the inverse, I don't remember how it needs to be. I didn't pay too much attention to that detail, but it's really a beautiful paper. So you can express the inverse of a matrix in the same format as
It's the inverse or an approximation of the inverse?
the exact inverse.
Typically, one way to compute the inverse is to apply the power method.
Exactly. And the power method, once you get to powers, you are back to this. And this is 1 by 1 minus a. So you can express the inverse using those techniques. Just mind-boggling.
And you can do eigenvector computation. It's exactly this E star times translation.
Much fun.
All right, thank you. We'll be back.